On to this evening's programme, or this afternoon's programme, and our first speaker is the winner of the Women of the Future Science Award. I would say that she's very much a scientist of the present as well, and that's Dr. Karen Masters from Portsmouth University. I remember a very excellent NAM from July last year, so Venue Cymru is going to have a hard act to follow. And she's going to talk about Galaxy Zoo science, revealing the impact of galactic bars. Over to you.
Hello everyone, it's a pleasure to be here. I gave a similar talk to this about 4 years ago at an ordinary meeting, and it was a great pleasure in preparing for this talk to find out how much more we had done in the following 4 years. So I'm delighted to be talking about this today. So I realised after I had prepared the talk and put it on the system, I didn't actually say anywhere in my talk what a galactic bar is, but luckily I've put a picture of one on the main first slide here. Oops, that's not working.
Sometimes a separate device.
Just like that, yeah. So this linear structure in the centre of this galaxy, NGC 1300, one of the galaxies with the largest bar known compared to the size of the galaxy, is what we think of as a galactic scale bar. And what I'm going to be talking about in this talk is Galaxy Zoo results on galactic scale bars in galaxies. That one's yours, so that's not going to work. Ah, right. There's supposed to be one, though. This one. It's much bigger looking. Excellent. Right, so hopefully in this audience, I don't need to spend too much time introducing Galaxy Zoo. It should be a pretty well-known project, I think, in the UK astronomy community. But just as a reminder that we're now approaching the 8th birthday of Galaxy Zoo. That's coming up this summer. Galaxy Zoo originally launched in July of 2007, asking members of the public to visually inspect 1 million galaxies that had been observed as part of the Sloan Digital Sky Survey main galaxy sample. Then a couple of years later, following lots of interesting science results from that phase of the project, it was realised that this was a successful method for quantifying visual morphology and actually could ask much more complex questions about the shapes and structures seen within galaxies. And so February 2009, we launched the second phase of the project with 250,000 Sloan galaxies, the brightest nearest 250,000, asking for much more detailed morphology. So we've since gone on to include public Hubble Space Telescope optical surveys, so things like Cosmos, GOODS, and any of the public surveys that you can think of. And the current site is running with HST Candles, which is the near-infrared Hubble survey. We've also had UKIDS images of SDSS galaxies go through the site, and most recently sort of branched out into radio astronomy, which seemed appropriate to be talking after the meeting about the SKA, but there's Galaxy Zoo Radio, which is exploring the cross-match between radio and optical or near-infrared morphology of galaxies, and just had the first couple of papers out from that project in the past couple of weeks. So that's a lot of different phases of Galaxy Zoo, and there won't be a test. I'm not expecting you to remember all the different phases, but I just wanted to point out we actually have a lot of different samples now that have run through Galaxy Zoo. And we're not done with galaxies yet. We have more new images that we're currently working on preparing for launch, some more candles, more HST. We're going to, for the first time, put in Sloan single filter images to try to quantify the effect of the change of wavelengths on morphology. And one thing that I'm really excited about, and a little sneak peek about this, is we're going to put images of galaxies that were simulated in the Illustrious simulation. These images now look very realistic. They look like real galaxies. And we're going to actually get quantitative visual morphologies of simulated galaxies so we can compare the morphologies of the simulated galaxies to the real universe in the same method. So I'm really excited about that, and stay tuned about that. And more still. We're not done yet. So I often get asked about this, and this is the only thing I'm really going to say about the Zooniverse. So it was 2010 that the Zooniverse launched off the back of the success of Galaxy Zoo, and the Zooniverse is now much, much bigger than Galaxy Zoo. It now has 1.3 million users and runs more than 30 projects, with plans afoot to make it a flexible system that could launch hundreds of projects a year over the next few years. And this is way beyond astronomy, right? This is all types of academic research. So it's really crowdsourced analysis of data from ancient papyrus to World War I diaries, whale song, penguin watching. And there's a really neat new project that just launched last week looking at Victorian science journals and actually looking for images in them called Science Gossip, which is actually really fun, even for me. So that's sort of the impact of Galaxy Zoo on wider society, but I'm not here to talk about that. I'm going to talk actually and change gear and talk about our astronomical science results. In the universe as a whole, we're really proud of a philosophy of publishing based on the citizen scientist inputs. So Galaxy Zoo is leading the way of the sort of school chart of publications from different Zooniverse projects. We now have 56 officially, but of course we've got ones in the works that are about to be submitted, so we now have more than 56 peer-reviewed papers. So it's no longer really possible to give a talk like this, talking about the overview of all Galaxy Zoo science, so I had to pick a topic. And I decided the topic I wanted to talk about, the one that I've spent probably most of my time working on, is what Galaxy Zoo has told us about galactic bars. So just a primer on how we find bars with Galaxy Zoo, a reminder of the method that we have. So we're showing people images of galaxies and we're asking them a series of descriptive questions about what they see in the galaxy. And we collect 20 to 40 answers typically, sometimes up to 80 per galaxy. We want n independent answers where n is large so that we can do averages. We call this the raw vote fraction, so the fraction of people that said one thing versus another is the raw vote fraction. We then apply some weighting by user consistency, so we measure how good people are compared to the sort of bulk or compared to a set of gold standard images. So we can downweight very inconsistent users, so people are coming in and clicking randomly, school children who don't understand what you're asking them to do, or people trying to maliciously upset our research, I don't know. It doesn't matter what you do, if you do it inconsistently with what is actually seen in the image and everyone else does, you will be downweighted and it won't matter, it won't affect our results. We also correct for observational biases, so the fact that galaxies that are further away look smaller and dimmer. And this really has to go on a survey-by-survey basis. So all of those different surveys that go in are going to have a different observational bias correction. And then finally, we're left with these debiased classification likelihoods. So we don't have an answer for a galaxy. We basically have a series of numbers that tell us how many people or how likely we think it is that that galaxy has a certain type of morphology versus not having that type of morphology. So this is an example classification of a galaxy that I picked out to have a very strong bar. It's a very small picture, so I apologize for that, but you might have to take my word for it that it is an extremely strongly barred galaxy. This is a new visualization that Coleman Krawczyk has been working on. He's working with us in Portsmouth. And we think it will go at explore.galaxyzoo.org and let people really play with this, hopefully soon. But the Zooniverse team are a bit distracted with stargazing live right now, so you won't be getting anything out of them for a while. Anyway, this basically demonstrates the path that the majority of users have taken through the classification tree for this galaxy. And so you can see up here, this is the weighted votes. So we've downweighted inconsistent users, which is why we don't have an integer number of total users starting, but we've got 39.019 people once they're weighted. Looking at this galaxy, 38 of them say they see a disk, 37 of them say the disk is face on, and 35 of them say there's a bar. 36 of those 37 said they saw spiral arms, and so on and so forth. So you get a sense of how we're getting this morphological information from Galaxy Zoo. There's no accounting for people. There's always people who pick the inconsistent answers, or there often is. But by doing this statistical method with large numbers of people, that doesn't matter. We get the right answer. So P bar will come up a lot. P bar is just the number of people who said there's a bar compared to the number of people who were asked that question, which is 37. We only ask people if they can see a bar in a galaxy if it's a disk galaxy that's face on. So P bar for this galaxy is 35 over 37. Sorry, I did do the sums right despite not writing it right, which is 0.95. And of course, we're not just taking this on trust, right? We actually compare our bar classifications with bar classifications from other places. And so this is a comparison of our bar classifications with bar identifications from a catalogue that was published in Naya and Abraham in 2010. So Preeti Naya was a graduate student who actually, I believe she told me once, when she had a broken arm, sat down and classified 15,000 Sloan galaxies twice over by herself. And she classified galaxies as not having a bar, disk galaxies as not having a bar, having a strong bar, an intermediate bar, and a weak bar. And these distributions, so the distribution of that galaxy zoo P bar, so from no one saying they saw a bar to everyone saying they saw a bar in these different categories. And you can see we agree very well. In Prithi's no bar class, basically all of our P bars are below 0.2. In Prithi's strong bar class, we're all above 0.8, and even in intermediate bars, everything's above 0.5. Weak bars, we don't see much of a trend of P-bar in Prithi's weak bar classification. Maybe this is a bit subtle for our Galaxy Zoo users. But I will just make one comment that in the galaxies which Prithi said had no bar, but we have P-bar of 1, I've looked at them, they all have bars. And the ones where we say, Prithi said was a strong bar and we have very low classifications, I've looked at them and they don't have bars. And this is not to criticise what Prithi did, which was outstanding and I think on the mean very, very accurate. But individual people are subject to error. And so those galaxies probably represent mistypings that she made. When she's doing 15,000 galaxies, you can't really blame her. And there was another sort of expert classification that we also compared our bar vote fractions to. This was the Fiji sample published in Byler et al. 2011. It's kind of a Galaxy Zoo inspired method. They actually had 3 to 5 expert astronomers classify using a web interface the galaxies and make a different set of classifications, and they've put together these classifications. One neat thing was that they made an estimate of the length of the bar relative to the galaxy. So an Fiji bar length of 1 is, they're saying that the bar is basically the whole size of the galaxy, and 0 is no bar. And so one interesting thing that we haven't used too much in Galaxy Zoo yet, but the Galaxy Zoo 2 bar vote fraction seems to correlate with the length of the bar. So where a bar is very, very large compared to the galaxy, P bar will be very large. Everyone sees the bar. And where there's no bar, no one sees a bar. But in intermediate ranges, there is a correlation between the bar length. So an intermediate or a weak bar that stretches some fraction of the galaxy, not right across the galaxy, will have some intermediate value of P bar where some people saw it and some people didn't. So how did we get interested in bars in galaxies? So I started working with Galaxy Zoo Project when I first moved to Portsmouth about 7 years ago now. And at the time, we didn't have Galaxy Zoo 2. We had no bar classifications from Galaxy Zoo. And I got interested in the red spirals, so spiral galaxies that are as red as ellipticals but show really clear spiral structure. And actually, it was a summer student working with me on this project that we published in 2010 that commented that all of the red spirals that he'd been flicking through appeared to have bars. And was that unusual? Did you expect that all of them should have bars? And we sort of looked and we said, well, we're not quite sure. Why don't you classify them? We didn't have Galaxy Zoo 2 yet. So he sat and he classified all 300 red spirals as whether or not they had a bar, and a mass match sample of blue spirals whether or not they had a bar. And we found that the red spirals were 4 times more likely to have bars than the blue spirals. So this seemed very interesting, and we thought maybe we'd like to pursue it a bit more and actually look in a statistical sense. Galaxy Zoo 2 was about to be ready to start using for science, and so that was really good timing. And so this was the first paper that came out from Galaxy Zoo 2 in 2011, where we plotted the fraction of galaxies in the Galaxy Zoo 2 disk galaxy sample that had a bar as a function of their optical colour. So this is the fraction of face-on disk galaxies that have a p-bar greater than 50%. So there's a lot of fractions in there, right? But I basically said, if your p-bar is greater than half, you definitely have a strong bar there. And then I'm calculating the fraction of galaxies that have that, meet that criteria. So we saw this really clear trend that red disk galaxies were much more likely to host bars than bluer disk galaxies. And this was a little bit contrary to some other published trends of a bar fraction with colour at the time. And it turned out that a lot of that was due to the fact that a lot of disk galaxy samples are actually colour selected. So they're actually picking blue galaxies and then looking at the bar fraction in blue galaxies rather than disk galaxies. And so they're actually missing a lot of this part of the trend. And this has now been sort of confirmed. It was also seen in the RC3, so back when that was visually selected again, not doing the colour selection. Naya and Abraham saw the same thing in their sample, and there was another more recent one that saw the same thing with a different bar identification method. So what should a bar do? So this was really interesting, right? This seems to link bars with the process which is stopping star formation in disk galaxies. So what should a bar do to a disk galaxy? Well, in order to answer that, we need to think about basically some basic physics. It's really nice physics, really nice classical dynamics when you're talking about bar dynamics in a disk galaxy. Basically, the bar enables an exchange of angular momentum. Because it breaks the symmetry, it allows angular momentum to be transferred outwards. So usually you have a transfer of angular momentum outwards beyond this point, which is the co-rotation point. So this is the point where the orbits of the stars orbit at the same speed as the pattern speed of the bar. And inside there, you have a negative transfer of angular momentum. So angular momentum is transferred so that the stars and gas move inwards. Sorry, the gas moves inwards and the stars move outwards. And so you have this gas funneling into the center and the stars moving outwards as the bar lengthens over time. It's a fairly classic just disk instability. If you have just a flat disk of stars floating in space independently, it will be unstable to collapsing inwards. And actually, it's a really neat thing that the fact that there are galaxies that don't have bars and yet are stable is an indirect evidence for dark matter halos. There must be a stabilizing large halo of material stopping that disk from collapsing inwards. In theoretical models of bar growth, this transfer of angular momentum and material obviously means that the central concentration in a galaxy will grow. This can fuel central star formation since it's primarily gas that's being transferred in. And there's been discussions about fueling of AGN as well. Obviously, the scale of an accretion disk of an AGN is much, much smaller than the galactic scale of these bars, so that requires further inwards transport. But you're certainly getting a lot of gas into this central region. Would this use up atomic gas more quickly? Once you increase the density of atomic gas, you have much more star formation and you can actually use it up more quickly. And you're evacuating the space around here as well from atomic gas, so you're removing it from the rest of the disk. And there's this funny thing that there's actually a positive angular momentum transfer beyond co-rotation. So there are suggestions that could actually be preventing infall of external gas. It's hard for the gas to cross co-rotation, or things happen to it at the point of co-rotation that make a little bit of a potential barrier. And then there's this controversy, are bars self-destructing? Do they basically drive all the material in and then dissipate and then reform? Or do they maintain over a Hubble time? And you can find theorists who will argue vehemently for both sides of the argument still. So I think that the jury is out on that, but they certainly seem to be very long-lived. Gas is very important in this process. I've talked about it quite a lot. And the first simulations of galaxies that included or attempted to include gas, cold gas, were not able to form bars. And just to point out that none of these effects are included in any semi-analytic models of galaxy formation. So these might all be there in mass scalings with other stuff that's going on, but all of these clear effects, clear physical effects that bars have on galaxies are not included in any of those models. Anyway, back to Galaxy Zoo, when we wanted to test some of these things, what's going on. And so one of the things that I really like doing is observing neutral hydrogen. That's one of the forms of cold gas in a galaxy. And there's this survey, Alfalfa, which is run by my former thesis supervisor, Martha Haynes. It's an Arecibo blind H1 survey, and it's surveyed about half of the sky that the Sloan Digital Sky Survey imaged. So about half of all Galaxy Zoo galaxies are in the footprint of Alfalfa. At the time we did this work, which was published in 2012, we had access to the 40% Alfalfa data sample. And of all of the face-on disk galaxies in Galaxy Zoo that were in the Alfalfa footprint, about 2,000 of them were detected in H1. So we start with 1 million galaxies and we come down to 2,000 where we can get both the measurement of the bar and the neutral hydrogen. I don't know how familiar everyone is with what a H1 single dish measurement is, but Arecibo is vast. This is a kilometre around the disk, so it's a 300-metre disk. But the beam of it is much larger than all galaxies in Galaxy Zoo. So basically you get a single piece of information about how much hydrogen there is in this beam. But because it's a spectral line, we also get frequency, we get the kinematics. And so what you get is you get this classic H1 profile where the central velocity of the galaxy is in the middle, and you see these peaks from the rotation of the galaxy. And what we found was that, as is predicted by theory, there were more bars where there's less gas in galaxies. So gas-rich galaxies had a lower bar fraction, so this again is bar fraction up here, now against gas fraction. So the gas-rich galaxies have a lower bar fraction than the gas-poor. And we reproduced the optical color trend that we saw in the larger sample, and also this is stellar mass. But there's a well-known correlation between the amount of neutral hydrogen in galaxies and their stellar mass. So what is the driving correlation here? Is it that galaxies that are more massive have more bars and they just happen to have less gas? Or is it that galaxies which have less gas have more bars and they just happen to be more massive? So if we plot this H1 gas fraction against the stellar mass relationship for our 2000 galaxies, you get this approximate trend. The orange are all the points, a point for every galaxy, and the contours show the bar fraction in big bins on this diagram. And I think you can see even by eye that the bar fraction peaks below the line. So this is galaxies that are less H1 rich than is typical for their mass. So H1 astronomers call this the H1 deficiency, where a positive deficiency is less H1 than is expected for your mass. And so we can see that there's a higher bar fraction on average in galaxies with less H1 than expected, and a lower bar fraction in ones with more H1 than expected. So there's definitely a residual correlation between bar fraction and atomic gas. And we tried to split it up a bit more. So this again is bar fraction against stellar mass and against gas fraction. And now the red and blue in this case are gas rich and gas poor. And the red and blue here are actually optically red and optically blue. And you can see, the least massive in terms of stars, galaxies are all gas rich, and the most massive are all gas poor. But in the middle, there's this transition regime where you have the same stellar mass but different gas fractions. And you see you're always more likely to get more bars in gas poor galaxies at the same stellar mass. So it really seems that it's the atomic hydrogen content that's driving the correlation between bar fraction and stellar mass. And similarly, on this side, there's a range of gas fraction where you have a sort of overlap. You have some red galaxies and some blue galaxies, and you're uniformly going to have a higher bar fraction in the red galaxies than the blue ones in this sort of overlap regime. And so we suggested this was a hint that the bar was actually stopping the galaxy from forming stars at the rate that you would expect for its neutral hydrogen content. It's not conclusive, but it's a hint that that's happening. So stay tuned on that. We've still got some VLA data actually to look at the pattern of the gas relative to the pattern of bars. Because H1 rich galaxies with bars are quite rare, there's actually not many resolved observations of H1 in strongly barred galaxies. So looking forward to getting that reduced. So here's some work from Edmund Chung, a very talented young postdoc now at IPMU, where he's using the Galaxy Zoo bar classifications and trying to look for evidence of secular evolution. So if you focus on this central panel from his paper published in 2013, this is the specific star formation rate of galaxies plotted against the Cercic index of galaxies. So this is a measure of the shape of their light profile, where large Cercic indices correspond to very big bulges, classic bulges, and small Cercic indices correspond to small bulges or pseudo-bulges. If you look on the star-forming sequence, you can see, so the colour is the average bar likelihood in bins. So it goes from blue being unlikely to have bars to red being most likely to have bars. And if you look just on the star formation sequence, you can see there's this trend where bars, as a galaxy is more likely to have a bar, it moves across to higher Cercic N. And so this is interpreted as evidence that the bars in these galaxies are actually building the central bulges. So it's the first real good observational evidence of secular evolution in the Galaxy Zoo sample. We saw hints of it earlier in 2011. So this is just the straight bar fraction as a function of colour, but now split into galaxies with big bulges, which are blue and green, and small bulges, which were the red and green, and the small bulges are the blue and black. And you can see that for disk-dominated disk galaxies, they have low bar fractions right across up until they're very, very red. Whereas for bulge-dominated disk galaxies, they have high bar fractions right across the colour. So again, this is evidence of bars being involved in processes that are building bulges. How much time do I have left? I always run out of time to explain this properly. About 3 minutes, yes. As is typical, I've completely run out of time to explain Ramin's extremely nice work on marked correlation functions with bars, where basically the summary of this work is that there's evidence that bars are more strongly clustered than other spiral galaxies on certain scales. And intriguingly, We also see evidence that bars are less likely to be present in galaxies that are closely interacting. So this again is from Galaxy Zoo. So we have this picture where bars might be triggered in mild interactions and then get destroyed in more dramatic interactions. But there is definitely correlations going on with environmental processes and the triggering of bars. Finally, so looking out at Galaxy Zoo Hubble, and so moving out of the local universe, we find that bars are more common in dynamically mature galaxies. So it means in the local universe we have a higher bar fraction than we see out at high redshift. So this is now bar fraction as a function of look-back time, or redshift, from the Galaxy Zoo Hubble sample. This is work done by my student Tom Melvin, and this very clear decline. And then moving out into Galaxy Zoo Candles, work by Brooke Simmons, showing so the black points now from Candles showing that this low-level bar fraction seems to persist way out beyond redshift 1. And the grey sort of hash line here is the only theoretical model that predicts what should happen to bars, which predicts they should drop off to 0 beyond redshift 1, but with a very large error. And then got to have a shout out to the most recent results that we have of Bars Fuel AGN. I mentioned this early on. So this is some work by Melanie Galloway. And basically, if you just do a simple plot of AGN and bars, you'll find more AGN where there are more bars. But this is just all driven by the fact that both AGN and bars are more common in more massive redder disk galaxies. And if you correct for that, you've got a maximum of 16% of AGN in the local universe can be triggered by bars. And we see similar results at high redshift. When you control for the stellar mass and the colour of the galaxies, there's no enhancement of AGN fraction in barred galaxies in our Galaxy Zoo Hubble results. So the green and the purple here are statistically indistinguishable. So despite this lack of link between bars and AGN growth, it is possible to grow black holes in galaxies that cannot have had any mergers. And so this is an example of a galaxy that Galaxy Zoo has identified as having absolutely no central bulge. Also doesn't have a bar, we note. This was published in Brooke Simmons' work in 2011. And we're having some fun with crowdsourcing and Stargazing Live coming up at the end of next week. We're going to try to have amateur astronomers image this galaxy and then add up all of the images that they all take and see if we can get a deeper image than this of this individual galaxy. So we have no idea if this will actually work, but it's an interesting new foray into crowdsourcing for Galaxy Zoo. So I'm sure I should end now. And you don't get to see the future, so I'll just have to say thanks. The future is big, bright.
We do have a bit of time for some questions. So, Miles,
I think you should make an effort. May I suggest you make an effort to see galaxies in which you're seeing the bar end on, because this will tell you a lot more about the dynamics that are going on. And I maintain that the bar is straight because it's self-rotating about its long axis, and this is dynamically keeps the system straight.
Well, we're going to have the dynamics of lots of bars soon, so it gives me a chance to mention my slide about moving into the third dimension, so getting lots and lots of spectra across galaxies. So we'll get dynamics of lots of bars that way. And so we'll see.
I'll send you the image of one that certainly is doing this.
Okay.
Yeah, that's really good work. I was wondering about something. You said that bulges might be built by bars, but bulges typically are pretty old. And you said that the gas moves in, but the stars move out along the bar. And so I was wondering, is the idea then that the gas forms new stars in the center, and that's what builds the bulge? Or? So
I'm being a bit loose. So there's two kinds of bulges. There's what we call classical bulges, which are old, and there's these pseudo bulges, which maintain some they typically rotate. They're typically not as de Vaucouleurs-like in their profile as a classic bulge, and they're typically younger. And so it's really those pseudo bulges that bars would be building, not the classic, very old bulges, definitely.
Which way round does the secular evolution work? Are the bars preventing stars from forming, or have all the stars formed in a starburst, used up the gas, and those are the galaxies which then develop bars? You know, Are the stars forming the bars, or are the bars stopping the stars?
So I'm beginning to dislike bimodalities in astronomy and these either-or questions. And I suspect the answer is that, yes, both. So, yeah.
Okay, I think time for one more over on the side there.
You should get in politics for answering in vague ways. More general question about Galaxy Zoo. How's the popularity going over time? Because, when something new comes up, it's popular, then people tend to stop using after a while. So I was just curious, what's the long-term viability?
So the Zooniverse was always set up with this idea of becoming media independent, that the Zooniverse would build this community of people who like doing citizen science, and that then doesn't matter if you get on Stargazing Live and things, you've got this community. And there's good evidence that's working. The Zooniverse users just grow linearly, which is typical of social media growth. Every time a new project launches, you get more users to all projects, pretty much. There's a few exceptions to that. And Galaxy Zoo maintains its position as one of the most popular of the projects. Planet Hunters is pretty popular, so we have a little astronomy war, but no, not really.
Okay, thanks very much. Let's thank Karen again for a great talk.